Welcome into the second video for Calc 3 material. Right, so we're going to introduce the concept of a vector. Right, now a vector is just a mathematical object that has both a magnitude and a direction. Okay, so think about like particles. Particles have a direction that they're traveling and also how far they travel. Let's go over some of the notation. There's a few different notations that we can see. Right, so first, right, will be a U with a bar over it, or with an arrow over it, right? And it has these carex denoting that it's a vector. Say this is a two-dimensional vector. We have U1 and U2. Right, so maybe you'll see the arrow over it. You may also just see it in bold. Now I can't write in bold, obviously, but you get the idea. So this is one possibility, right? What else? What else can we add here? Another possibility, so I'll add two more things here, and then we'll get into discussing what they look like. We could also see this in IJK form. So let's say vector U is going to be equal to, and there'll be some constant, right? So let's just say A1, or we'll use U1 here. We'll use U1I plus U2J plus U3, let's say, K. Right, so this would be a three-dimensional vector. And I'll give us some examples here. So let's give some examples. So let's go with a two-dimensional one. What does this look like? And I'm going to call this one V from now on just to differentiate. So let's say we have V, which is a two-dimensional vector, and we have 1, 2. Right, so this is a two-dimensional vector. All it's saying here is that we're moving to the right 1 and up 2. So let's get a visual at what that looks like. So I'll draw a graph here. Now for a vector, right, it does have a starting point and ending point, but we don't really care about the starting and ending point. So I'm just going to draw it from the origin, and I'll explain why in a second. So let's say we go over 1 and up 2, and we draw a line, and we're going to call this V. Now we say we'll say two vectors are equivalent, we'll just say equal, if they have the same direction, I'll just put same direction, and the same length. And so what's being mentioned here, what's not being mentioned here is the starting or ending points, right? All I care about is the same direction, same length. Meaning, right, if something has the same length and it is parallel, right, then we would say they are equivalent. So let's say I have another vector, and I'll try to make it parallel. That looks something like this, and pretend these are exactly the same length. We'll call this one W. Right, these two would be equivalent, right? So if they have the same length and the same direction, they're equivalent, right? The initial point, right, which is what this is, the starting point is known as the initial point, and the ending point, which is known as the terminal point, are not really that important when seeing if vectors are equivalent. Right, so initial point where we start, terminal point where we end. All right, so hopefully that gives you an example of what this looks like. Again, the first component just telling us where we're moving, right, as far as the x value, or x direction. Second component, the y direction. Imagine if we had a third component, right, the z direction. Now, as far as this notation here, right? This is normally known as, I call it physics notation. I'm probably calling it something wrong, but physics notation. Right, so an example here would be, let's say u, since we're using the same thing, is equal to 3i, let's do minus 2j plus 5k. And to me, this is, I mean, as far as calculating, this is not a very useful structure to give me, right? So I'll admit, anytime I get physics notation, I'd go, well, let's just put this in a notation that's really actually going to be helpful here. Right, 3, -2, and 5. All right, I, J, K, we don't need letters when we're trying to do calculations, so we'll just get rid of the letters, 3, -2, 5. Right, so we have both forms of our notation here. There is one more thing that we want to mention before we move on to the next part of operations, but it's very nice when they give us the vector, right? We have the vector, it's given to us. Same thing here. What if we want to create a vector? Right, meaning, what if I gave you 2 points in space, say A and B, and I say, go create me a vector, right? Well, in this case, right, not too difficult, right? Not too difficult, so I'll give you 2 points. Let's say I give you point A, I'll draw a little line here. Say I give you point A, and what would this be? This would be somewhere around, let's do -1, comma, -1. And I give you point B. And where would that be? Let's say this is like 3 and 2. Right? And I want to find the vector, right, from A to B. Right? And so what I want to do, if I want to create the vector, I call this from A to B, and this would be the notation you would see, is I'm just going to say, well, this will be equal to my terminal point, right? So you want to start from the end and subtract the beginning. So 3, right, my terminal point, minus -1, which will be +1. So 3 minus -1. And also, right, for my y component, the same thing. 2 minus my other -1, so +1. Was that 3? Oh, this is, that's okay. This is not a -1, this is a +1, isn't it? Okay, so let's mix this around. Sorry guys, no one corrected my graph. This should be a -1. There we go. I was like, wait, this is positive x's. So yeah, +1, -1, b is going to be 3, 2. Okay, so when we go to find the vector connecting these two, we do our terminal point, which is 3, minus our initial point, which is 1, +1. So now we have 2, comma, 3. All right, so again, if they give us a vector, great. It's going to be very nice to perform operations. However, if they don't give us a vector, it's not too difficult, right? We're just subtracting values to find, right, the separation. And again, this is just telling me 2 in the x direction and 3 in the y direction, right? It doesn't really matter the starting and ending point, right? We don't have that information here in the vector. It just gives us a direction and magnitude. Right now, it doesn't look like it, but it does, right? We could construct what the magnitude of this vector will be, right? The length of it, we'll get to that later on. And we obviously have a direction, right? Because it's 2 and 3. All right, so that's good for now. We'll talk about operations of adding vectors together, as well as scalar multiplications. So I will see you shortly. Now that we have a concept of what a vector is, let's go ahead and add some operations. First one being vector addition, right? And this one's very intuitive, right? The same way you would normally add up stuff, we're going to use the same method, right? So let's say u is equal to little u1 little u2. And again, we have the carex to denote a vector, and we'll do the same thing here for v. v1, v2. We add them up just by components, right? So u1 plus v1, right? Same components. And u2 plus v2. Easy enough, right? Exactly how you would think. So let's do an actual, there's something else I want to mention with vector addition known as the parallelogram parallelogram law. So we're going to do a drawing over here. So let's go ahead, we'll do an example. Let's say u is equal to, we'll do 1, 2, and we'll say v is equal to, let's do 3, -5. Awesome. Okay, and before we even draw, let's go ahead and calculate. Let's just add them up. So u plus v is equal to 1 plus 3, 4, 2 plus -5, -3. Awesome. Okay, now I want to go ahead and graph all of these things and see how they fit together geometrically. So let's go ahead. I think we're only dealing mostly over here in quadrants 1 and 4. So let's go ahead, we'll do u plus v first. So 1, 2, 3, 4. 1, 2, 3, 4. -3, good. Just double checking. Not bad. I'm going to put u plus v just here so we know. Right, so now we have that one graph. Let's go ahead and do u first. So we'll do u is 1, 2. All right, 1, 2. And we'll draw a line from the origin to u, and I'll put u here so we know. Okay, so now the idea is, for u, I started at the origin, but now when I add v, I want to have my initial point starting at u. Right, so I'm just going to start at u. So again, I've performed u, right, the u vector, and now let's just tack on v to the end of it. So starting at our point here, let's go over 3. So 1, 2, 3, so I get to 4. And I go down 5. And I end up exactly where my u plus v vector ends. Right, so this is v. Right, so this is all that's happening. I've applied the u vector, and then to the end of the u vector, I've applied v, and I get my u plus v. And it doesn't matter which order we go. Right, so imagine now, let's see if I can do v first. Right, so imagine now I do v first. Right, so I'll go 1, 2, 3, and down 5, 4, 5. So I have a vector down here. So we'll draw this, and this won't be perfect, but you'll get the idea. All right, this is v. And then I add u to the end of v, and I go up 1, 2. Well, what happens? Again, I end up here, so this is u. Now again, this isn't perfect. This should be a perfect parallelogram. My drawing's not the greatest, right? This isn't to scale. I think my 1, 2 is stretched out too much compared to my 5 down here. But you can imagine this would have a symmetric drawing, right? So this is the parallelogram law that goes with it. But again, vector addition, very intuitive, just adding component-wise. You can imagine if we extended this into 3 dimensions for a vector, right? It's going to be the same, right? You're just going to add component-wise, but I'll specify, right? So if we had, I'll do a different one. Let's do A, even though we don't normally use A to denote a vector. And it has little a1, little a2, and little a3. And let's say we have a b vector, and we'll have little b1, b2, and b3. Right, if we add these two together, it should be intuitive that we're just adding component-wise. Right, easy enough. Okay, so that is it for vector addition. We're going to add another very nice, easy operation, scalar multiplication. We've probably already seen it again if we've taken a physics class, but I will be right back and we will discuss scalar multiplication. Welcome back for a section on scalar multiplication with vectors. So we'll just say scalar multiplication again, another very intuitive operation, scalar multiplication. And we're going to say, right, so I'm going to use some math notation here and I'll walk you through it. So I'm going to grab a scalar or a number, right, and we'll just say this scalar is C. And it's going to be coming from the real number. So I'll explain this. I'm just making this harder than it really needs to be, but just so you guys see some math notation, this is saying a scalar C is coming from within. This is in, and then this, of course, is the real number. So choose any real number is what this is saying. And all this means is if we take this scalar C and we multiply a vector, right, u2, and I'll write this backwards, but this is equal to, this is C times our vector u, right? Well, all we have to do here is just multiply it in, right? We just get, it's very intuitive, C times u1, comma, C times u2, right? It seems easy enough, right? There's nothing to it. Again, this notation here, think of this like a weird E, right? It's just saying in. There's a scalar in the real numbers, right? And if we want to multiply it in, it just gets multiplied to each component, right? So I'll draw a graph over here. Let's go ahead. We'll keep using this color. We'll do a few examples. Ooh. And let's just take vector u to be equal to, let's just do an easy 1, 2. I don't know why that 1 is so tall. And let's say, so we'll go ahead, I'm going to graph u. So let's say u is 1, 2, 1, 2. We put a dot, we graph it. Boom, this is u. Right, what about if I want, let's do 3u. Well, easy enough, right? We just multiply it in. 3, 6, right? 3 times 1, 3. 3 times 2, 6. And what do you think the vector looks like over here? It just gets scaled up. So the direction doesn't change, right? It just gets scaled up. So 2, 3, 3, 4, 5, 6. And so it should still be here. It just gets extended to the top. All right, so this would be u. This would be 3u, right? Now, only one other really interesting thing here is what if we multiplied by, let's say, a negative scalar? What does this mean? Well, let's just calculate it, right? We get -2, -4. So we're in quadrant 3. It just goes the other direction. So if we multiply by a negative scalar, the vector is just going to go in the other direction. So -1, -2, 1, 2, 3, and the arbitrary 4 hanging out here. We'll put a point, right? It just goes in the other direction. So it changed the, sorry, stop here. We changed going into the other direction 180 degrees, right? And we scaled up by a distance of 2. All right, so really that's all we need to talk about as far as scalar multiplication, right? The next part of this video will include magnitude as well as unit vectors, so I will see you there. All right, last part of the video. So when we first started talking about vectors, we said they had two things. They had direction, which we're not going to talk about for right now, but they have magnitude, right? Or in other words, length. So how do we find the magnitude of a vector? Well, let's say I have some arbitrary vector. We'll say little u1 and little u2 as the components. And I'm only going to draw it in 2 dimensions. This idea will extend up to 3 dimensions as well. But what's really happening here? What is u1 and what is u2? So let's go ahead, we'll do a drawing over here. Ooh. And let's just say this is u, right? This is u. Well, what's happening here with u1? What is u1? Well, u1 is an instruction on how far to the, right, how far on the x-axis we travel. Assume this is a positive value, right? So we travel to the right u1 distance, and we travel up u2 distance. Right, so these components are actually representing lengths here, right? So what do we have? Well, we have a triangle. What do we know about a triangle? Right, well, we know the Pythagorean theorem. And in this case, just so we're clear, I haven't denoted what magnitude is. Right, the magnitude notation looks like this, right? Bars around it, right, saying find the length of the magnitude. Right, well, what is the length of the magnitude? It's this distance here. It's the hypotenuse of our triangle, right? Well, I know the Pythagorean theorem, right? And I also know the distance formula. It's all the same. So all I have to do here is go, well, I could square it, right? I could square it for right now if I just want to use the Pythagorean theorem, right? A squared plus b squared equals c squared. So this is u1 squared plus u2 squared. But again, if I just want to find the right magnitude, I take the square root. This will just be equal to the square root of u1 squared plus u2 squared, right? Now you could take the same idea and scale it up, right? Just in case you're wondering, what do you mean? Well, if I had 3 dimensions, we'll call this v here, right? 3 dimensions, we'll say little v1, little v2, little v3. What do you think that looks like? Well, the magnitude of v will just be the square root of v1 squared plus v2 squared plus v3 squared, right? We won't draw the 3-dimensional version of this. We did this previously when we went over distance formula in 3 dimensions. Same idea, right? Let's do an actual example and we'll have one more concept to construct. So let's go ahead. If I give you a vector, let's say I'll write it over, where shall we write it? We'll write it over here. Right, so I'll give you a vector, let's say v, or we'll call it w actually, and we'll just say this has, right, the components of 2, and we'll say -5. And I want to go find the length of this vector. Well, the length of this vector is just going to be equal to, what do we have? The square root of 2 squared, 4, plus -5 squared, 25, which is just going to be equal to the square root of 29, right? So that is the magnitude of our vector. Easy enough. All right, so now that we have the direction, right, the magnitude, I want to introduce one new concept on top of this. So let's draw a line here. And we're going to call this, or we're going to call these unit vectors. Now, the only thing, or the definition here of a unit vector is a vector with length 1, or magnitude 1. With, I'll just say length of 1. Right, it has a length of 1. How do I go about creating a vector with a length of 1? Well, if I give you a vector, right, and I want to turn this into a unit vector, so we can use the same example that we already have here, right? I gave you the vector 2, -5. How do I turn this into a unit vector? Well, all I have to do is, I'm going to denote it as u sub w for unit vector of w. It's going to be equal to w, right, the vector w divided by the length of w. That's it, right? Take your vector and divide it by the length of itself, and you should have a unit vector. And let's go ahead and check, right? Let's go ahead and check since we already have it. Let's say, well, this is going to be 2, -5, all divided by square root of 29. And we're going to want to just distribute this root 29, even though it's ugly, to each piece, right? So to each component. So this is going to be 2 over root 29, comma, give you a chance to catch up as well as for me to switch markers, negative 5 over root 29, right? And maybe some of you are like, I don't believe you. That's not going to work. Why would that have a length 1? Well, good thing for us, we know how to calculate, right, the length of a vector, right? So let's take this vector and we'll calculate the length of it and see what happens. So if we, see if I can get a little low here, if we calculate the length of u sub w, this is going to be, right, u1 squared, so the square root of u1 squared, and let's go ahead, we'll write this out, 2 over root 29 squared plus negative 5 over root 29 squared. And we'll move forward, right? 2 squared is going to be 4. And a square root squared will just be 29. And same thing over here, plus 5 squared, or negative 5 squared, 25, over square root of 29 squared, 29. And what do we get? 4 plus 25 equals 29. 29 over 29, 1, square root of 1, 1. So indeed, it is a unit vector. Right, so again, just to recap everything, we'll talk about direction in the next video. We're just talking about magnitude for now. We are using essentially the Pythagorean theorem, right, or the distance formula on top of that to find the magnitude of our vector. And once we have the magnitude, we can now have this additional resource of constructing unit vectors, in which you just take your vector, divide it by its length, and you have a unit vector. Maybe some of us are wondering, why do we want to do or calculate a unit vector? When it comes to computation, having a length of 1 for your vectors does make calculations easier for, let's say, computers, right? So that is the whole general idea. When you get into linear algebra, working with vectors there in vector spaces, you'll have a similar idea that you'll bring up, right, when you're working with unit or length 1. So that is it for this video. Until next time, I will see you. Feel free to leave suggestions, comments, questions, anything you got in the comment section, or I will see you in class. See you guys.